Thank you. Hi, I'm Zhijie, and I'm from University of Arizona, and I work with Beth Hellman in the Social Pixel Lab, and this work is like a joint contribution between me, Rohit, Anna, and Jonathan. Um, so yeah, let's get started. So what I'm doing here is I'm trying to map flood impacts using multi-sensor data fusion in urban areas. Uh, yeah. Okay, so actually, a study conducted by Best shows that satellite imagery shows that increasing population is moving into the floodplains, and more population will be exposed to flood in the next decade. And this map is actually it just shows that. So basically, any place other than the yellow place and the gray one shows that there's going to be increasing population and probability of people being exposed to flood. So it becomes more increasingly important to map flooding urban areas for disaster assessment and mitigation. So what am I trying to do here? So the goal of this project, which is funded by NASA THP project, is to produce a daily flood extent probability map in urban areas to better monitor and capture the max flood extent. There are many challenges. The first challenge is because the heterogeneous nature of the urban areas. First, it's very complex. There's a different drainage system and there's impervious surfaces. So this kind of requires because like we're trying to use remote sensor imageries to map the floods. So this requires like very high spatial resolutions remote sensor imageries. We can see from this graph that on the very left is the image from PlanetScope, which is a 3-meter commercial sensor. And we can see some traces of streets and buildings. But even if the spatial resolution downsides to like 10 meters, it's pretty hard to tell like what is actually underneath that. And if we're using traditional, like the most used, one of the most used sensor like MODIS, it's 250 meters, then we cannot see there's anything underneath. So yeah, that means like we need to use very high spatial resolution data for this job. And the second challenge is the temporal coverage. So this graph shows the image availability during a flood event in San Pedro Sula. So the first row is the Sentinel-1 availability. We can see that there's not that many. And the second row is Sentinel-2. MODIS is there every day, but also like I mentioned, it's 450 meters. So you can actually use it in the urban area. And Landsat is 30 meters, and it also has a more force, a temporal availability. And even planets doesn't have that much covered in this region during this flood event. And this is the precipitation, like accordingly to this flood event. And we can see the peak actually happened over here. So what this shows is that like basically like using just one sort of sensor, there will be a huge gap. And so what we're trying to do is to kind of combine different sensors to kind of make this gap smaller. And one thing that I want to mention about Planet is that so they launched the Super Dove sensors in 2021. So the image availability has become much better after that. And also like they included more bands because before 2021 they probably they only have 4 bands, RGB and near band. After that they have 8 bands. So that's a huge improvement. And the second challenge is the spatial coverage. So for example, like if we want to continuously just monitor one area, even though like there might be like the general sensor coverage in that entire region, but for many spots, we cannot guarantee we have observation every time there's a sensor pass. So this is an example. Like we can see that in this region, there's like sensor overlap from November 19th and November 27th. But on the November 25th, there's basically no overlap of this area. So it's going to be impossible to monitor what's happening over there. So in conclusion, like using satellite data, no single product is sufficient. Not just because of the things that I brought up, but also about the nature of sensor itself. For example, there will be trade-off between spatial, spectral, and temporal resolution. And like for Sentinel-1, it can penetrate through cloud, but the distortions in urban areas and spectral noise is going to be an issue. And for Sentinel-2, it's multispectral, but also it's optical sensor, so there might be a lot of cloud. And for PlanetScope, yes, the cloud is still going to be there. and also it's commercial. So like you have to pay to actually access that data. So what we propose is to use to first fill information from different sensors to first make those gaps smaller. And then we try to develop some algorithm to fill in a spatial temporal gap that I just mentioned. Okay, so this is a pretty big project, so there are many steps to actually achieve our goal. The first step is to curate a high-resolution urban flood data set. I mean, there are a lot of the data set because okay, so we're trying to use deep learning and we're trying to develop models. So the data is very essential. And because of the specialty of urban floods, we need a kind of specific data set to actually do it. There are other data sets, like one is actually also from Best company, Flood Street, it's flood based now. They created Sentinel-1F11 data sets, but it's not focused on urban events. And also there's not an impact data set, there's XBB, but they do not focus on urban events. So we curated a high resolution urban flood data set based on planet-scope imageries. And there are 14 urban flood events that occurred during 2017 to 2020. And then there's in total of 320 1024 by 24 pixel size chips using planet-scope images. So all those chips, they are manually labeled based on 3-meter resolution sensors. And this like 320, this number might not look so big, but because they're like 1024 by 1024 compared to other data sets, which is usually 512 or like 256, it's actually a pretty big data set already. And there's actually one more thing, because this part of labeling is not led by me. It was led by Rohit and Hannah in our group. One more thing that we actually have more data sets. So this data set is actually led by me. It's called Flood Planet. It's kind of have the same nature, but we don't focus on just the urban flood events. And there are 19 flood events and 365 labeled. And also like what's special about this is that we also downloaded the corresponding Sentinel-1, Sentinel-2, and that's eight images for each label. That's kind of temporarily closed because each sensor they have different times. So we can make sure that they all captured from the same day, but we make sure that or we try to make sure that the most difference is 3 days and at the same location. So that's what we did. And so how did we label those manual labels? We hired these 10 students and basically did this process for a year and a half probably. So this is what we provided them. First, the pre-flood true color composite image from PlanetScope, and then the flooding image true color composite, and also the force color composite, and the flood normalized difference like NDWI, and then like the gradient labels like that. So we actually use the 2 different labeling tools to do this labeling process. The first one is called Labelbox. It's open source and it's pretty easy to use, but they do kind of updates a lot. So sometimes there's a new feature that I don't know. So after 1 month, I feel like everything is new. And the second one is the NASA image labeler. The reason, okay, so the Labelbox is used on the THP project, which is the urban flood dataset. And the NASA image labeler was used on the Flood Planet. The reason why we use 2 different platforms is because the second project we have collaboration with the NASA impact team. So, and they tend to use that. So that's why we went with that. But we actually have even more data sets. We also have one data set that contains 90 permanent water chips, also 1024 by 1024. And we also have another data set that's labeled based on Black Sky, which is also a commercial data set that's but has much higher spatial resolution of 1 meter. And so adding all of those, on that we spent about 1.5 hours per chip. And so basically the initial labeling process was about 15 minutes and 30 minutes to review and adjust them. So that means in total of about 1,300 hours was spent on this. So this is in the duration of 1.5 years. So that was a lot of label work and a lot of management. But the good news to everybody is that we will release those data sets. The urban flood data set will come a little bit later because we just started writing the paper, but the flood planet that I mentioned is gonna come out pretty soon because we're already doing internal review on the paper. So hopefully the reviewers will not be so harsh on us and we can publish sooner. Okay, so the second step is that we use the label data set to train models to detect urban flood from different sensors. The model that we use is the typical UNet. This graph actually shows the original style of UNets, but we actually did something a little bit fancier. It's like we added just a bunch of different things to make the model perform better. I will not go deep into that. So basically, what the model do is that we input the image, and then it gives us the segmentation result. So that means like we assign a class to each pixel of the input image. And here's something that we found. So after those experiments training those models, we evaluate our Planscope models for spatial generalizability. Right, that was kind of long. So what that means is that we have 14 flood elements, right? So we use 13 of them to train and using the one lab to validate the result. And so basically we did that for 14 times. So that means every region has a chance to be left out. And so I think this is a more fair way to represent the actual performance of the model rather than just randomly pick some testing data sets. Like no surprise, Planscope had pretty good performance compared to other sensors. For example, here's the actual hand label, and our model was even able to detect a lot of the details and also text to units. And also like from here, it's kind of a cross-center comparison. Hand label, there's a lot of details here. Planscope was able to detect some of them, or say most of them. But if we do that on Sentinel-1, a lot of them are lost. And the last part of the last row is actually the performance. So we can basically say the performance in each reading is pretty good. And we also evaluate accuracy across public and commercial sensors. Like I mentioned, like we use the labels on Planscope and Sentinel-1, Sentinel-2, and less than 8. This result is actually not from this urban flood data set, it's from the flood planet. Because in the urban flood data set, we didn't like include these many sensors. But we can still see something from this urban area. This is the urban area in the flood planet data set. And we can see the Planscope was successful to capture those smaller detailed features. Sentinel-1 and Sentinel-2 could not do that. Yes. And so one thing that we kind of find is that the data quality scales better than data size, which was kind of the deep Google memo on large language models. Yeah, so we actually did experiment because I mentioned there was a lot of data sets, right? So we tried to not just use the urban data set to train the model, but also add the other data sets like the Planscope and the permanent water. But the thing that we found is that after adding the other data sets, the result never got better. There was always about 1 or 2% of a decline in the performance. So all the result that I'm going to show later is all going to be based on just training based on the urban flood data sets. And I think the reason why is because the nature of the flood and the topography, that basically everything in urban flood is quite different from the more general flood, because the other data sets might be in a more rural area and that does not have so much buildings, so many infrastructure. So that could be the reason to confuse the model. Here comes the last step is so we have the model, we have the data set, we have model that can actually infer those flooded areas from a single imagery. The next step is actually to fill in those gaps, right? So what we're trying to do is that we develop a spatial temporal algorithm to fill in the gaps with the help of topography features like elevation, slope, to the right hand, height above nearest drainage, and also the spatial temporal data. Even though they're very close, modest, and weird or obvious, even though they're very coarse, but the advantage is like what I mentioned, we have daily access to them. So we are hoping that they can still provide some information to that. And also the temporal data, which is precipitation, soil moisture, and brightness temperature. We're not just using the data from that day because flooding is a process, and we try to basically include the information from what happened before that into that day. And here is the very preliminary stuff that I'm doing now because I just finished building that kind of data set, and this experiment is I've been only working on this part for like 3 weeks, so a lot of results are very preliminary, and there might be a lot of flaws, but we're actively improving because it's a 3-year project and we're only a year and a half, so that means I still have a year and a half to make improvements. So yeah, so using the model that we trained, I formed a time series spatial temporal data set. Which means I use the models trained from the step 2 to run inference on any data available from any sensors during the flood events to use as weak labels. Even though we want to use the actual manual labels, which we're supposed to have, I mean, it does have higher quality, higher accuracy, but it's a luxurious thing. Like I mentioned, we use a year and a half to get those many labels, but if we want to actually label so many different timestamps, it's impossible. So we have to use weak labels. And there's also a lot of literature shows that training on weak labels and fine-tune on actual manual labels can improve the model. So that's one reason too. And I also collected, processed, and the corresponding topographic data, coarse resolution, optical data, all the stuff that I mentioned. This was a very long process, and it's all about the data process. So it was not very fun, but the real fun part starts from here. So basically, what I'm trying to do is that this model structure is inspired by change detection and video frame interpolation algorithms. So here's the general idea is that let's say like we have a gap data, we have all those gaps that I mentioned before, but we definitely have the information from the time before that and time after that. So the general idea is to use those information, including the information that's on the gap date, whatever information that we have, to infer like what happened during the gap date, what's the condition over there. That's the general idea. And I can show some very preliminary results. This result might change a lot in the next 6 months, but this is what I got so far. So basically, I use the time. So this is the actual planet scope image input into the model, and this is the weak label, which is the label they use to actually train those spatial temporal models. But those weak labels are from step 2 that we use to detect those flooding area from the image. And the last row, the last column is the actual prediction. So we can see that in general, just looking at those numbers, it performs fair. I would say it's still fair. But one interesting thing is that in these dates, 11/19th, November 19th, there was a lot of cloud coverage. And so the actual the actual flood detection model only detects a very small fraction of flood area, but just judging from what happened before that, which is November 15th and November 25th, this area should still be flooded. But because like the second stage model relies on satellite observation, so it was hugely affected by cloud. So it only detected this much. But our inference model, which is how the spatial temporal model thinks what happened during these dates, actually successfully predicted that. So that's a good sign. And this also shows in here, we can see that this is the precipitation of this region in the monsoon region. So actually this thing it was already flooding even before this, which is why we can see flood over here. And at this date, November 17th, there was another big precipitation. So our model, which is the red line, the spatial temporal model, was successfully kind of fit the line of what happened with the precipitation data. And note that this is even the result without inputting the precipitation data. And the actual satellite observation actually didn't do a very good job because of that. So that was the first try, and the next thing that I want to add is the actual temporal data into the model, because the previous model, it basically only takes the day before and after that, and kind of infer the medium state of what might happen between that. But we do not have a timestamp. We do not know like what exactly happened at the day that I want to see. So the next step is to add those temporal data into the model. And also because there's a lot of resolution difference in the different source of data. So we will try to use a late fusion approach to basically let the model do some layers of pooling first, and then add the lower spatial resolution data into the model to kind of make the resolution difference a little bit better. And that's about it. So thank you for attention. And from the Social Pixel Lab, and this is the link. So if you guys want to follow the work, especially the release of the data set and everything, follow this, and hopefully at least the flood plan data set can be released in the next 2 months. And probably in the next 4 months, hopefully we can release the urban flood data set. Thank you.
Thanks for the presentation, Zhijie, and great that you're putting all this data out there for everyone to use.
Yeah.
Are there some questions? Please, Ben.
So thank you for the talk. It seems that many pixels would have different confidence. For example, filled in pixels, your confidence would be lower. How do you deal with that later when you use these images for modeling?
So I think that's inevitable because like the model can only perform to one extent, and also like I mentioned, we want to use the all manual labels, but it's not possible. So we can only work with whatever we have right now. And the issue that you mentioned is definitely going to be there. And I think that the one way to actually make it better is to improve the flood detection model on the second step to make the whole prediction much better, have less uncertainty.
And thank you. And a small follow-up question, like in the released data sets, the flood planet and the urban, would you add metadata for each pixel, like mask for each pixel if it's filled or not?
Yes. And actually, we actually have a certain class which is on dirt and water, because even for human interpreters, it's very difficult to actually see like some areas if it's actually flooded or not. So there's actually three classes. One is the place that we are sure it's flooded or it's from the water. That's one class. The second class is observed water. And we actually running a lot of experiments to try to explain what those observed water means. But it's very difficult because we have 10 labels, right? And each label has their own preference. They're human too. So we're not sure like how much that will come into the uncertainty of those labels, but we're trying to quantify that. So that's a progress. Thank you.
Maybe a final question before the coffee.
Yeah, just quick question. So in the figures that you showed, they're pretty small, so it's hard to tell, but we saw a lot of permanent water being classified there. So the question is, in your analysis, are you masking those out? And if you are, how confident are you that you're really capturing the urban? Because it was hard to see, but it didn't seem like there was a lot of like deep urban classified flood water.
Yeah. So like when we're actually running the model, we will mask out the actual permanent water parts. That's the first question. And for the second question, like like I also have some thoughts about that, because like how do you define an urban area? So the way that we use it, we use the dynamic word land use and cover classes, and if that indicates that that area is urban area, then we will say it's urban. But like I mentioned, there's a huge variability between each chips. In some chips, there's full of buildings. But in some chips, there's only few buildings. So, but in general, like the principle that we follow is first the dynamic world land use land cover. And the second one is that we make sure that at least those regions are in the range of the urban area.